So this is going to be a little bit different from the presentations you've seen so far. We're going to look at data more in aggregate. And this is work that is essentially supported by something called the hydrogen pipeline, the pipeline blending CRADA. CRADA means Cooperative R&D Agreement. And this is a work funded by the US Department of Energy. I don't usually put this slide first, but I know a lot of people are taking pictures. And if there's any picture you should take, it's probably of this slide. Probably not going to be a lot else that's of that much interest. And since I usually run out of time, I have this slide at the end, but you may not get to see it, depending on how things go. So I thought I'd start with that. Oh, I should mention, this is our team. These are the folks really that make the magic happen in our laboratory. These are some informational resources that we maintain. And I'd like to point out Helper. Actually, you could, during my talk, you could actually download this software if you like. I did it this morning. It took me about 5 minutes to actually run a simulation. This is the URL to get the software, but this software essentially allows you to do structural integrity calculations for things like pipelines. It's intended to be a probabilistic fracture mechanics tool, but you can also use it for deterministic studies and sensitivity studies. So you can look at how does a pipe perform in hydrogen based on uncertainty, for example, in the pressure cycle and other things. So this is technically my title slide, hydrogen-assisted fatigue and fracture of pipeline steels. That's what we're going to look at. As I mentioned, as the slides were coming up, this is work that's part of our pipeline blending CRADA, which is often referred to as high blend. And really the aim of that project is to develop the scientific framework to enable hydrogen blending into natural gas infrastructure, or even conversion of natural gas infrastructure to pure hydrogen use. So you see a little schematic here of what a natural gas system looks like. We're looking at both the transmission, the high pressure side, as well as the low pressure distribution side. This is a large project with a lot of different national labs contributing to it. I'm only going to talk about the part that happens in my team. And that work is really on the compatibility of steels. So there are three principal parts of that. I just mentioned the part of developing this probabilistic open source GUI-driven software for doing structural integrity analysis. There's another component where we've developed a subscale pipe testing system. So this is sort of meant to be a complement to full-scale testing. Full-scale testing is very expensive and time-consuming. In this system, we can test up to 60 millimeter diameter pipe. We can engineer defects into that pipe, and we can pressure cycle until failure. We use that system to address things like oxides. For example, we've done pressure cycling of pipe with the native mill scale on the inside of that pipe. We put a defect on the outside of the pipe. We pressure cycle with hydrogen, and it turns out that hydrogen actually gets through that native oxide, segregates to the stress intensity ahead of that notch, initiates a hydrogen crack that actually propagates from the outside in, and the pipe fails. So this is a demonstration that your oxides are not going to prevent hydrogen embrittlement in a real type of pressure cycling scenario. But the part I want to talk about today is quantifying the critical parameters associated with fatigue and fracture. So that's what I'll talk about. Folks who are interested in this program, you can get more information at this email, which was on the first slide as well. This is somewhat of an open program. It's a partnership. We have, in the first phase, we had over 30 partners as part of that activity, and anyone that's interested to join is welcome to join that project. All right, so we've seen this a few times before this week, sort of standard Venn diagram. The way we use this in our work is we think about what are the sort of material variables that we have in these types of materials, what sort of things can change, and how do those impact, for example, the fatigue and fracture process. We think about the environmental variables, and we try to decouple all these things so that we can try to identify trends associated with some of these different critical parameters that affect the fatigue and fracture. And so that's what I'm going to talk about. I'm going to try to separate some of these different parameters so that we can study them in a more fundamental way and look at them in aggregate to see what sort of general trends can we identify and apply widely and develop tools such as the helper tool to help us do assessments in sort of the general case. I was talking this morning with some folks. For example, if you're putting in a pipeline, it's not one material. It's literally hundreds of materials if it's a long distance pipeline, right? You may have seals from half a dozen different mills in that pipeline. And so we need generalized tools that we can use to do these sorts of assessments. So we're going to talk briefly about some of the materials variables. I'm going to focus on strength. I'm going to focus on partial pressure. Unfortunately, I'm not given enough time to talk about impurities, but I'm certainly happy to talk about that offline. And then the mechanics of the problem is embedded in just about everything that we do. All right, so this is an image from our laboratory, what this system looks like. We've heard several times this week that testing in hydrogen gas is hard, it's expensive, it's not safe. I'm going to be provocative. You're probably going to disagree with me, but that's okay. That's why we're here, right? To exchange ideas and to challenge one another. And I will challenge you by saying that I actually think testing in gas is not only safer, it's cheaper. If I think about all the studies that I've seen this week on electrochemical methods, if I took all those resources, I could have built dozens of these machines, right? Doesn't make sense in my mind to do it halfway, do it right the first time. If you don't believe me, ask Boeing. If you know what's going on with Boeing, they've been doing a lot of things halfway these days, and they're having a lot of problems. It would have been much cheaper to do it right the first time. Now, with regard to safety, one of the advantages of a hydrogen pressure system is that you can engineer safety into the system. That's incredibly important. We engineer safety into all of our systems. So what we're effectively doing is we're taking out the human factors. The most hazardous thing you have in a laboratory is the people. So the human factors is the biggest problem that you always face in the laboratory. And in these kinds of systems, you can engineer that out of the problem. If you're doing wet chemistry, you cannot do that. There's no way you're going to get around people splashing acids and moving chemicals around and all those sorts of things. That's going to be the most dangerous thing you're going to do in a laboratory. And I think if you look at incidents in laboratories, it bears that out. Wet chemistry is probably a lot more hazardous, or in my mind, it's a lot more hazardous than a well-developed and designed and engineered pressure system. So in my view, it's much cheaper, safer, and more effective if you're interested in studying gaseous effects on materials to actually build a proper system. So this is what our system looks like. Here's a schematic of what it looks like in a cutaway with our specimen in the middle, where this volume is pressurized. This particular system operates at up to 1400 bar. We are often doing it at much lower pressures. What are some of the important elements of a system like this? Instrumentation is key. All of our instrumentation is internal to the autoclave. So we're measuring displacements on the specimens, for example. I've seen a number of studies this week where folks showed what they called a tensile curve, and it showed that the yield strength was around 2% strain. That's not a metal. They didn't have the right instrumentation in those measurements. So that's a key element of our system, we believe, is the robustness of our transducers that we use in the system. We use direct current potential difference for all of our testing. What this means is in a fracture test, we can get the full JR curve, not just 10 or 25 points, but literally thousands of points if we want to sketch out that JR curve. So we do all our testing according to standardized test methods, accepted fracture mechanics test methodology. That's really important. There are some other things that you need to worry about with hydrogen, things like frequency, for example, and strain rates. Don't have a lot of time to talk about that. Again, I'm happy to talk about those sort of elements offline. So we use ASTM E647 for all our fatigue testing. We use ASTM E1820 for all of our fracture testing. Why? Because all of these materials are ductile in hydrogen. I know Milos would describe some of these fracture surface as decohesion. They're still very ductile. And so we cannot do linear elastic fracture mechanics, generally speaking, on pipeline steels. It needs to be elastic plastic. And then the environment, of course, is very important. You know, high purity gas as the input is key, but it's not enough. 5 minutes already. Jeez.
5 minutes left.
Yeah. So gas impurity is critically important in terms of your tests, but it's not what you put in, it's the environment that the specimen actually sees. So it's critical that you measure the hydrogen inside your test chamber, the quality of the hydrogen. And you need to have oxygen typically below about 1 ppm. All right, so it's not really an innovation, but one of the ways that we're able to get the data that we do is by being very efficient with our testing. And so one of the things that we do is we do K-controlled fatigue tests. And that allows us to do these different segments of increasing K, decreasing K. We can do that at different R ratios or stress ratios, which allows us to generate an awful lot of data from a single specimen. We execute these tests such that we end at a low K, which then allows us to do a fracture test at the end. So in a single specimen, we can generate a whole number. I mean, here I'm showing 4, it could be many more, just depending on the conditions, of fatigue crack growth curves in a single specimen, and then we can do a fracture test at the end. So I need to speed up a little bit. So this is just an example of a few steels that we've done, noting some of the differences between vintage and modern steels. Carbon's pretty high in vintage steels compared to modern steels, as is sulfur, for example. Lots of different microstructures we've evaluated, ferrite perlite, bainite, acicular ferrite, all the usual things. So what does this look like? So let's start with some of the materials things. So what I'm showing here is fatigue crack growth as a function of stress intensity, classic way to show that. I'm showing 5 different grades of API steel from X52 to X120. They all fall on top of one another. There's no strength effect in fatigue crack growth, at least down in this region. You have to worry about exceeding the fracture toughness. If you go to too high of a delta K, you will exceed the fracture toughness, and then it's no longer a fatigue test. So if you're going to delta Ks of 80 or something, I would question your data. Over here, we see modern and vintage steels. So there's over a dozen different steels. You see they're more or less the same. Looks like actually that vintage steels might be a little bit better. We have an explanation for that, but that's a different topic. Fracture toughness of all these different steels. So here I'm plotting the fracture resistance as a function of hardness. And as you might expect, at least at the bottom end, there's sort of this general trend of reducing fracture resistance as the hardness or the strength goes up. These two points here represent the X100 and the X120. These represent simulated welds where the welds are overmatched, so the welds are over hard, to try to understand how those microstructures are affected by hydrogen. You can see the fracture resistance gets quite low, down in the 30s. So you can't do fatigue on this in delta Ks of 30 because you're above the fracture toughness. Pressure is another variable that's really important. People often ask me, is there a critical pressure below which hydrogen doesn't have an effect? And the answer to that is no. As someone once told me as they were trying to understand this and get their mind around this, they said, so what you mean is the first molecule is the worst molecule? Absolutely, that is the case. So this red curve here represents testing in 1 bar hydrogen, for example. This blue curve represents testing in 200 bar hydrogen. These dashed lines are actually the ASME design curves, which are, these are the new ones in the code case, and they show those curves are sensitive to pressure. So there's a pressure term in there, which is embedded here. So actually, we need to use the fugacity, and it turns out that the relationship between these curves is the fugacity to the square root. Here's the fracture. So these are JR curves for this is actually a vintage steel at different pressures. And again, you can see that even at 1 bar, you see a very substantial reduction in the fracture resistance. And it continues to go down as you go to higher pressures. And so this is just like looking at that same data another way. And what I'd like to point out to you is this black bar represents a modern steel in air. This is a vintage steel in air. And then these are the values in hydrogen. Now, if I express this with an embrittlement index, what would I see? I would see that the modern steel is much worse than the vintage steel. Is that true? No. Look at the values. What we need and what we design to is the intrinsic fracture resistance. The fracture resistance of the modern steel is better. So you need to be very cautious using these embrittlement indices. If they have the same reference point, that's one thing. If they don't have the same reference point, as in this case, you'll get exactly the wrong idea about the data. So another really critical point in my view. All right, quickly wrapping up here. So this is just an example of mechanics variables. I'm not showing data, just to make it a little bit simpler to see what's going on. This is the design curve from ASME that was developed. There's a term in here for the load ratio, and that's shown here, just plotting what that relationship looks like from the code to show you the effect of the load ratio or the stress ratio on those curves. And then this is the pressure term. So we can generate these same curves at many different pressures. We have data from 1 bar up to 1,000 bar, and these relationships are based on that data and are captured, and these design curves capture a vast array of data. All right, so quickly, just to summarize, hydrogen-assisted fatigue and fracture is sensitive to these different categories of variables: materials, environmental, mechanical. Tried to break down and show a couple examples. For example, materials. Fatigue is not sensitive to strength. Fracture resistance is. We've developed and show the effects of pressure or fugacity on fatigue crack growth. There's an effect on fracture as well. I don't have time to talk about oxygen and oxides. We have a lot of data that shows there's no benefit of those things on the long term. You might see a very short-term experimental benefit, but remember, we're dealing with infrastructure that's going to be in the ground for years. And then finally, fatigue is in hydrogen is much more sensitive to things like the stress ratio and frequency. So we need to carefully consider those. I'll stop there.